Okay, so it looks like we have our second presentation set up here. So Sushata Subedi is with Louisiana State University and is going to be talking about the evaluation of raw bagasse ash as sand replacement for the production of engineered cementitious composites. So please go ahead.
Thank you, Susan. Thank you, Susan. Hi, everyone. I'm Sujata Subedi. I'm a PhD student at Department of Construction Management at Louisiana State University. Today, I'm going to present on a research conducted at LSU, which is titled as Evaluation of Raw Bagasse Ash as Sand Replacement for the Production of Engineered Cementitious Composites. Before I begin the presentation, I would like to acknowledge the co-authors of this paper, which are Gabriel Arce, Dr. Marwa Hassan, and Hassan Nurband. So with this, I would like to start the presentation by briefly discussing about the ECC materials, ECC cementitious composites, also referred as ECC. ECC is a novel class of a high-performance fiber-reinforced cementitious composites, which are designed based on micromechanics and fracture mechanics principle to exhibit the high tensile ductility at a relatively low fiber content, which is typically 2% volume fraction. This material is also referred as a bendable concrete. Moving on to the properties of ECC, from this figure, you can see that the ECC materials exhibits multiple steady-state microcrack instead of a localized macrocrack as observed in concrete or regular fiber-reinforced composites. This behavior of ECC is referred as a pseudo-strain hardening behavior, which gives rise to an exceptional high tensile ductility, which is in the range of 1 to 8% strain capacity. In addition, this material also exhibits high flexural strength that is in the range of 2 to 3 times of the regular concrete or fiber-reinforced composites. Even though with these exceptional characteristics, the application of these materials has been limited due to its high cost and low practicality when compared to a regular concrete. This is primarily because it utilizes a manufactured microsilica sand, which is both expensive and is not readily available. Next, it utilizes a high cement content and it has a 2% volume fraction of polyvinyl alcohol fiber. Both of these materials increases the cost of ECC. As such, there is a need of a low cost and readily available ingredients that could partially or completely replace the microsilica sand or cement in ECC materials. At the same context, sugarcane bagasse fiber is a byproduct of sugarcane sugar production, which is widely available worldwide. Approximately 760 million tons of these materials is produced each year globally, where 90% of these materials are burned in the sugar mills and used as a source of energy. And the rest are disposed in land as shown in these figures, which has been creating the disposal problems and the potential fire hazard. When these sugarcane bagasse fibers are burned, they produce sugarcane bagasse ash, referred as SCBA. Potentially, there are nearly 23 to 68 million tons of these materials being produced worldwide. In the same context, the total cement production in US is nearly 88 million tons. So this signifies the right use and the right application of this material. From previous literature, it was revealed that this material is mainly composed of silica, carbon, aluminum oxide, and calcium oxide. As such, they present a potential to be utilized as supplementary cementitious materials. However, at the same time, this material also has high carbon content, unburned particles, and large particle size to be used as a supplementary cementitious materials. Nevertheless, when these materials are further burned and ground, they are likely to produce a material of SCM quality. As I mentioned earlier, the implementation of ECC is hindered by its cost and practicality. Therefore, it requires a low cost and readily available ingredient to replace the silica sand and this cement. Right now, sugarcane bagasse ash is considered as a waste with no economic value, and based upon its properties and size, it presents an excellent potential to be utilized as sand replacement or cement replacement based upon the level of refinement. As such, the objectives of these studies was to investigate the feasibility of raw bagasse ash as a partial or complete replacement to silica sand in ECC materials and investigate its effects on the mechanical and physical properties of ECC materials. To achieve these objectives, the first phase was to produce the bagasse ash, which was done by collecting the bagasse ash from sugar mill and minimally processing it by drying and sieving it through number 20 sieve to remove the coarser impurities as shown in this figure. The sieved bagasse ash was then used as a replacement to silica sand in ECC mixtures. The raw SCBA was also characterized in scanning electron microscopy, X-ray diffraction, energy dispersive X-ray spectroscopy, strength activity index, and laser diffraction particle size analysis. In the next phase, raw SCBA was implemented to produce the ECC materials, and they were tested. For the production of the ECC materials, ordinarily Portland cement type 1, class F fly ash, river sand, and non-oil coated PBA fibers and raw SCBA was used. In addition, polycarboxylate-based high-range water reducer was used to achieve the required workability. A total of 5 ECC mixtures, including the control, was produced in these studies. 4 different sand replacement level, that was 25, 50, 75, and 100, was adopted to investigate the influence of raw bagasse ash. The volume fraction of fibers for all ECC materials were kept constant at 1.5%, and the water to binder ratio were also kept constant at 0.32. All the produced ECC mixtures were evaluated by compressive strength, uniaxial tensile test, single crack tensile test. I would like to mention that single crack tensile test is similar to uniaxial tensile test, except that a thin notch is introduced at the middle section to induce a single crack during the testing. This was performed to obtain the fiber bridging relationship and compute the ECC design parameters, which are fiber bridging capacity and complementary energy. To gain the insight into the durability, surface resistivity, and crack width analysis was conducted. Crack width analysis was conducted on the dog bone specimens after they were tested in uniaxial tensile test. Now moving on to the results from bagasse ash characterization, the SEM images of this material show that it is composed of various particles such as fibrous particles, spherical particles, prismatic particles, and significant amount of irregular porous particles. The quantitative mineralogical composition from XRD showed that this material is composed of 53% of amorphous phase. In addition, in the crystalline phase, the majority of the crystalline phase was quartz, which is a crystalline silica. The chemical composition obtained from the EDS analysis showed that this material is mainly composed of silica and carbon. In addition, it also showed that the total sum of pozzolanic components was 53%, which made the ASTM requirement to be classified as class C pozzolan. However, and it did not meet the strength activity index as per ASTM C618, which requires to be 75% to be classified as pozzolan. As such, these materials cannot be used as supplementary cementitious materials in ECC mixers. Next, particle size analysis obtained from the laser diffraction analysis showed that the raw bagasse ash is significantly finer than the silica sand. For instance, the mean particle size of the silica sand was 474 micrometer, and that of raw bagasse ash was 256 micrometer. Now moving on to the results for ECC mixtures, the compressive strength at 28 days of curing in general decreased with the increase in the sand replacement level. However, the decrease in the compressive strength is minimal. For instance, at a 75% replacement, a maximum decrease of 11% in comparison to the control was observed. It is also important to mention that all of these materials obtain the compressive strength for normal concrete strength, which is 30 megapascal. This slide presents the tensile stress versus tensile strain for all the ECC materials. As you can see that all materials exhibited pseudo-strain hardening behavior. In terms of the tensile properties, all mixers implementing ECC exhibited higher tensile strength in comparison to the control, with the maximum improvement at 25%. In contrast, for fast cracking strength, all ECC materials exhibited lower cracking strength except at 25% replacement level. For tensile strain capacity, you can see exceptional enhancement in tensile ductility. For instance, at 100% replacement level, the tensile ductility is nearly 4 times 100 than the control. Overall, the implementation of raw bagasse ash enhances the tensile ductility without compromising the tensile strength. This slide represents the fiber bridging relationship obtained from the SCTT test. These curves were used to compute the fiber bridging capacity and the complementary energy. The fiber bridging capacity in general showed the similar trend as in the tensile strength. This is because the tensile strength of ECC mixer is primarily determined from the fiber bridging capacity. In contrast, complementary energy did not represent the similar trend as in the tensile ductility. It is because primarily at 75% and 100% replacement level. It is primarily because the tensile ductility of ECC material is influenced by both complementary and energy and the metric toughness. At 75% and 100%, it is likely that the metric toughness of this material was lower, which facilitated in the easy initiation and propagation of the cracks, thus resulting in the enhancement of the pseudo-strain hardening behavior and tensile ductility. In terms of the surface resistivity, a clear decreasing trend with the increase in the bagasse ash content is observed. However, even at the 100% replacement level, this mixture fall into the category of moderate chloride ion penetrability. Now moving on to the crack width analysis, as the replacement level of sand with bagasse ash increased, the number of the cracks also increased. The increase in number of cracks resulted in the significant improvement of the tensile ductility as observed earlier. In addition, all of the materials exhibited the crack width less than the 60 micrometer. As such, they are likely to exhibit excellent self-healing characteristics due to autogenous healing and are likely to be more durable than the regular concrete. So in conclusion, the raw bagasse ash used in this study consists of irregular porous particles with silica and carbon as its main constituents. However, this material cannot be used as SCM due to its high carbon content and low strength activity index. In terms of the ECC properties, SCBA decreased the compressive strength with the increase in bagasse ash content. Overall, in terms of the tensile performance, the implementation of SCBA enhanced the tensile ductility without compromising the tensile strength. SCTT results suggest that the enhancement in tensile ductility arises primarily due to a decrease in matrix toughness when SCBA is implemented as sand replacement. In terms of surface resistivity, SCBA content decreased the surface resistivity of ECC materials. The average crack width for all ECC materials were lower than the 60 micrometer, thus indicating the high durability potential. Based upon these properties of ECC materials, it suggests that the raw SCBA presents a promising material as a sand replacement in ECC mixers. Due to its readily availability and right now it is considered as a waste, this material is surely to enhance its economical performance as well. So lastly, I would like to acknowledge Tran-SET and LTRC for their support in this research. With this, I'd like to conclude my presentation and I'll be glad to answer any questions you have.